All right, hi everyone. Welcome to the morning session of the last day of the conference. The first talk of the session is on indistinguishability obfuscation from bilinear maps and LPN variants. And the authors are Seyun Raghavan, Nikon Vafa, and Vinod Vaikuntanathan. And Nikon is giving the talk.
All right, thank you for the introduction. Good morning, everyone. So what is indistinguishability obfuscation? It's a probabilistic polynomial time algorithm, I'll call it O, where the inputs and outputs are both circuits. And there's a correctness condition that says that the input circuit and the output circuit are functionally equivalent. And there's an indistinguishability condition that says that if you have two circuits, C0 and C1, and they're the same size and functionally equivalent, then their obfuscations should be computationally indistinguishable. While it might not be clear a priori, it turns out that this notion is extremely strong and is in some sense loosely crypto-complete. So with I/O and some other mild assumptions, you could build fully homomorphic encryption, adaptively sound zero-knowledge snarks for NP, succinct functional encryption, and much, much more. So much more that people often consider it to be a sixth world of impaliazos. The natural question is whether we can build it and realize it from reasonable assumptions. And I'll summarize the history from 2013 to 2020 as like a maybe as to whether we can build this with a series of constructions and breaks and back and forth. But then in 2021, Jane, Lin, and Sahai answer the question of can we build it with yes we can. Specifically, JLS 2021 constructed indistinguishability obfuscation from four assumptions. One being the learning with errors assumption, the second being a certain bilinear maps assumption, the third being large field LPN, learning parity with noise, and the last assumption being the existence of pseudorandom generators, or PRGs, in NC0 with polynomial stretch. Their follow-up work in 2022 removed the need for the learning with errors assumption, in particular getting the first construction of FHE without lattice or circular security assumptions. In our work, we replaced the last assumption, the PRGs in NC0, with a weaker assumption that we call local functions with noise. So let me reiterate, we take the JLS 22 construction and we've replaced the last assumption with something weaker. And what is this assumption? Local functions with noise? It could be described as follows. It says that there's some distribution over NC0 functions f going from n bits to m bits, where m is polynomially larger than n. And it says that if you look at a f applied to some random n-bit string, and you XOR it with some very sparse noise, so like inverse polynomial probability of each coordinate of the noise being 1, that should look pseudo-random. And here, just as a reminder, an NC0 function is one where every output bit of the function depends only on a constant number of input bits. So this is a very strong restriction on the class of functions f that we allow here. And I'll mention two possible ways to instantiate this assumption more concretely. So one is just plain old PRGs in NC0. And this would correspond to the case where there just isn't any noise. Like E is not even there and you just have f of s. And so think, for example, Goldreich's PRGs. So this assumption essentially says, as long as you believe that Goldreich's PRG is secure, if you add noise, that's enough. So here you can think of it as we're getting free noise to add in the assumption, which makes the assumption only more likely to be true. The second assumption is sparse LPN, where f is not only a local function in NC0, but is also linear over Z2. And this bottom footnote here, I just want to give credit to Ayush Jain, Rachel Lin, and an anonymous reviewer for suggesting the general perspective of LFN as opposed to just sparse LPN. Let me be more concrete about what this sparse LPN assumption would look like. It would look like a tall matrix A here, where every row has a constant number of non-zero entries, like think even just 3 non-zero entries. And then you have this like LWE style or LPN style sample with S and E described as before. And the assumption is that this should look pseudorandom. And because of this LPN instantiation of our assumption, we can interpret our construction, if you like, as a construction of IO from 2.5 assumptions, maybe. Why do I say 2.5? Bilinear maps is 1, and if you squint, maybe you can consider large field LPN and sparse LPN to be a total of 1.5 assumptions, because they both have a similar flavor, but up to you on that interpretation. Let me attempt in one slide to give a summary of JLS 22. And I'll emphasize here that this is simplifying, but hopefully it gets the big picture idea across of their construction. The starting point is using prior work to build succinct degree 2 functional encryption from bilinear maps assumptions. And here by degree 2 functional encryption, I mean that they're function keys for functions that are degree 2 polynomials over some ZP for a large prime P. Then JLS 22 use the large field LPN assumption and degree 2 functional encryption to upgrade it to some constant degree version of functional encryption. And their main technique, I'll consider it, or I'll call it algebraic compression. And I'll actually talk about this technique a little bit at the end of the talk. And then lastly, they use the PRGs and NC0 assumption to upgrade the constant degree functional encryption all the way to FE for all polynomial size circuits. And then using, and then the main technique going from constant degree FE and PRGs and NC0 is randomized encodings or Yau's garbled circuits. And then finally using AJ15, BV15 style bootstrapping theorems, we get from FE all the way to fully fledged indistinguishability obfuscation. And as a reminder, what we do is we replace the PRG and NC0 assumption with local functions with noise, LFN. And so how do we do that? Our main observation is that to make this transformation go through, we don't actually need a PRG and NC0 with polynomial stretch. We only need 2 weaker objects. One of these weaker objects is a linear stretch PRG in NC0. Think like a length doubling PRG in NC0. And thankfully, a work of Applebaum, Ashai, and Kushlevitz show how to instantiate this from the local functions with noise assumption. The second object we need, we call it a certain structured seed PRG that has constant degree over the integers and some small polynomial locality in M, where M is the output length of the PRG. And I'll be a little bit more explicit about what this means. But I just want to emphasize here that instead of locality O of 1, it's now like a polynomial locality. So the locality restriction is much, much weaker, but we still have a strict like constant degree over the integers requirement. What do I mean by a structured seed PRG? I mean that there's a seed sampling algorithm that outputs some seed sigma, where the sigma does not have to be uniformly random. And this whole algorithm, so in particular the length of the seed, has to be sublinear in M, the output length. And then the expansion function, the PRGG, expands from sublinear in M to M bits, has constant degree over the integers, and some small polynomial locality, as I said. And of course, we want it to be pseudorandom when applied to one of these seeds from the sampling algorithm. So how do we build it? What's a natural first attempt? One way to do it would be to try putting both the seed and the error vector, the secret vector S and the error vector inside your seed sigma. And then the evaluation would just be as the LFN assumption would imply. Do F of S, XOR it with E. Of course, what goes wrong here is that if you were to just write out this error vector in full, it would be M bits. And so in particular, this seed is longer than M bits, while the output is only M bits. So this isn't even an expanding function. But maybe you would think, well, this error vector E can be compressed somehow, right? But if you were to do it, compress it in, say, like the straightforward way of maybe writing a list of its non-zero indices, the expansion operation to get it back to a vector is not a constant degree operation. So what could we do? Is there some way to compress this error vector in a way that expanding it back is a constant degree operation? And we can do this, in fact, thanks to JLS. So they use algebraic compression to go from degree 2 functional encryption to constant degree functional encryption. Here we're using it to go from constant degree functional encryption all the way to full functional encryption. And they do it, in fact, in just degree 2, not constant degree. The key idea is to interpret this error vector E as a sparse square matrix. So here we're going to interpret it as like a root M by a root M matrix, where there are very few number of non-zero entries. And by very few here, I mean like less than the square root of M for now, let's say, just to make things simple. Because there are only like less than the square root of M many non-zero entries, its rank is also at most less than the square root of M, which means that it admits a matrix factorization over the integers where the width of U and the height of V is also less than the square root of M. The point here is that the total size of U and V put together is going to be also sublinear in M. And so this maybe we can now put in the seed of our structured seed PRG. So let me be concrete. What we're going to do is we have some seed sigma that's the secret vector, as before, along with this compressed version of the error vector, which you could think of as two matrices U and V from the previous slide. And then the G function is going to be exactly what we discussed before. You apply F to the secret vector, and you XOR it with E, where E is the matrix multiplication of the U and the V in the seed, and interpret that matrix once again as a vector. We should check its properties. The first is that this seed sigma can be computed in sublinear in M time, as we sort of saw on the last slide, so that's good. Moreover, I claim that this G function has the properties we want. And so why is it constant degree? It's constant degree because we're applying an NC0 function f to S, and because it's an NC0, it has a constant locality, which means you can arithmetize it to something that has constant degree over the integers. And then this error vector E follows from a matrix multiplication of U and V, which is a degree 2 operation. And XORing is also a degree 2 operation, and so this will work out. And finally, this will be pseudo-random from the LFN assumption. Let me conclude with some open questions and future directions. Naturally, can we minimize the assumptions of I/O even more than what we've done? Or maybe alternatively, is there any way to hope for an I/O construction that is post-quantum secure? Unfortunately, these constructions relied on bilinear maps, which is quantum broken. And lastly, is there any more cryptography that we can possibly build from the local functions with noise assumption? Or perhaps is there more cryptanalysis we can do to decide whether we can gain confidence in this assumption? That's all. Thanks so much.
All right. Thank you, Dekan. Any questions?
So why do you need sparse LPN over bits rather than over finite fields?
Yeah, the bilinear maps assumption gives us degree 2 functional encryption as long as the outputs are only bits. The decryption takes time proportional to the size, or sorry, to the number of possible number of possible values each output coordinate could take. So that's where we need it over bits.
Hi. On what region is this LFN believed to be secure?
Yeah, so I guess it'll certainly depend on this, on what functions you consider it with. But for the most general version of the assumption, I guess probably the constraint satisfaction problem literature would be the best place to look as to whether it's secure. I guess there's a little bit of a subtlety also in the distribution of the functions f that I've sort of hidden here. But if you consider, we don't know good deterministic ways to sample, sorry, not deterministic, but we don't know efficient ways to sample such functions. So to get sub-exponential security, say. So you have to be careful exactly how you do that. But assuming your function satisfies certain expansion properties, we believe it's sub-exponentially secure, assuming your sample complexity m is a small enough polynomial in n. Say for sparse LPN, if you like, if it's linear.